Welcome. In this video, we are going to take a look at multivariable limits. So limits are regularly at play in calculus, and for the most part, we typically have seen these in our introductory calculus course, often cordially referred to as Calc 1. So limits are always at play because when we take derivatives, when we take integrals, we're naturally making the assumption that the function is continuous. And when we're working with calculus, we're often making just these assumptions about limits existing in continuity, and we take that for granted often because not all limits exist, and if they don't, we can get into some trouble. Also, when you think about areas under curves, you're talking about infinitesimally small widths, and calculus 2, we're always talking about infinitesimally small, and we start to do that more and more in Calc 3 as well. So let's go back and revisit limits using some of our intuition and just trying to make sense of what it is that's going on when we talk about limits. So we defined for a function, y equals f of x, a limit as the value that y approaches. Okay, so that's key here. It's the value that y approaches, or seems to get infinitesimally close to, as x approaches some value a. All right, so we often write it like this, and this is just a really compact form for what we're saying in words up here. As x gets closer and closer to some value we specify, what happens to f of x? So I can draw a picture of a graph and say, all right, well, let's just say that right there is y equals 1, and we'll just define that as x equals 3. So our a in this case is 3, and when we take a look at this graph, we see that a limit does indeed exist because as we approach x equals 3, and we have to take into account the fact that there are two directions, we could approach x equals 3 from this direction or from this direction. So what I'm going to do is I'm just going to follow the path, and I'm going to stop when I get to x equals 3. So I'm coming down here, I see, okay, there I am. So I've reached a point, there's no hole in the graph, and so y equals 1 seems to be that value that I've reached. If I do the same thing coming from the right-hand side down the curve, and I stop when I get to x equals 3, I notice that those two curves come together. There's no hole in the graph keeping them from touching, and therefore we say that the limit, as x approaches 3, of the function f of x, so let's call this guy here f of x, is equal to 1. Now that could also vary because we may have a hole in the graph. So if we look at a similar sketch, but instead at x equals 3, we place a hole in the graph, okay, just like that, and we call this f of x. So again, x, y, and we'll use the same x equals 3 and y equals 1. Now if I follow from this side, I see that I am getting closer to that hole, right? And then I have to stop. I can't actually cross through that point. There's what we call a discontinuity there. It's a removable discontinuity, because if you just fill in one point, it's back. I would draw that circle kind of big to reflect the fact there is a hole in the graph, but it's really not that big. It's an infinitesimally small gap right there. So it seems like I got closer to 1, but I couldn't quite reach it. And from the right-hand side, I also approach y equals 1, again, as x equals 3. So because the value that I get closer to, the y value that I get closer to is 1 from the left, and the y value that I get closer to from the right is y equals 1, we say that, again, the limit as x approaches 3 of this function f of x is equal to 1. And so this is where the power of limits comes into play. We didn't say that f of 3 equals 1, right? In fact, here, f of 3 does not equal 1. That is, when x is 3, there is no output. There's a hole in the graph. So that means that the function is undefined at that point. But we can still talk about limits, because limits are about getting closer, making smaller and smaller, or making the step towards x equals 3 as tiny and tiny and tiny as we want. We can get infinitesimally close to that point. We'll get closer to a y value of 1, but we will never actually reach it. So here, in this example off to the left, f of 3 is in fact equal to 1. And this is what we call we say that this one here is continuous at x equals 1, and this one is discontinuous at x equals 1. So both limits still exist, one just has a discontinuity. So another way you might have heard this before is, I like to think about this as a roadway, and I'm looking at the roadway from a helicopter, right? And so for a function to be continuous at a point, I must be able to drive my car through the point without running into a big gigantic crater in the ground. I can't do that here. That's what we define a discontinuity to be. Here I can drive my car through x equals 3, and therefore this function is continuous. So there's the issues that we often get into are gaps or holes or just undefined intervals of a function. So we'll take a look at a couple more here just to make this more concrete, but just to give you some intuition. Now another thing that we could have is I'll draw one more here just to answer some of those lingering ideas or questions. So let's say that from the left-hand side the function looks like this, and I actually have at x equals 1, we'll say, a point. But then coming from the right, let's say the graph does this, and this one has to be undefined at that point because a function can only have one output for a given input. And so here I can't actually reach x equals 1, but I can get closer to it, and here I can reach x equals 1 and arrive at x equals 1. Now if we're driving down these roads, we said that in order for the limit to exist at x equals 1, the limit coming from driving from the left. Now I could drive from over here, or I can start here, or wherever I want. It doesn't matter how far you're able to drive to get that point. It just means that if you start anywhere and you start to trace that curve, where do you land? Well, here we land at y equals 3. But coming from the right, where would I land even though that discontinuity is there? Well, it appears that I would land at y is equal to 2. So we would write it like this. We would say that the limit as x approaches x approaches 1 coming from the left. So we put that little exponent, it looks like an exponent, it's a superscript of a negative sign, and the limit of this function as we approach 1 from the left, from the negative side if you think about it, doesn't mean you have to come from a negative x value, it just means you're coming from the left of it. From the left we said we get a y value of 3, but the limit as x approaches, as x approaches 1 from, let's try that again, the limit as x approaches 1 coming from the right-hand side of f of x, if we could get to x equals 1, it appears that our y value would be 2. So the limit exists. So first of all, we see the limits are different coming from two different directions. Therefore, the overall limit, the limit as x approaches 1 of f of x, so this is like a bidirectional, this means coming from both directions, is undefined. Okay, because the value that I would land at, the y value that I get from the left, is different than the y value from the right. Now the function is technically defined at x equals 1. F of 1 is in fact equal to 3, but all three of these numbers have to coincide. They all have to match in order for me to say the function is continuous. So here the problem is not that the discontinuity doesn't occur because of well, it sort of occurs because of a hole in the graph, but that every single x value in this graph does have a y value. The problem is we have this jump discontinuity, and this jump discontinuity creates differences in our limits. So there are different types of discontinuities. So this is a jump discontinuity. And this discontinuity up here is what we call a removable discontinuity, because if you just fill in that dot, you fixed it. Here you can't just fill in that point because you still have a big gap between your functions. So now that we have some of that under our belt and we've defined this in intuitive terms, let's define it in mathematical terms. So this is saying the exact same thing as what we said in words a moment ago. For the limit to exist, it must be the case that the value of f of x that you approach when x gets closer to a, coming from the right side. So I'll just draw a left arrow because this is saying we're coming from the right, moving towards the left. If that equals the same value of f of x that we approach if we come from the left to the right, then if these need to be equal, and they need to equal the same finite value, so it can't be infinity. If it's infinity, we say the limit doesn't exist, because a limit means it's a stop value. You think about what speed limit of 45 miles per hour is. It's a limit. That's as fast as you're supposed to drive. Whether you adhere to it or not, that's a different story. But in order for, if we said you can drive infinitely fast, well, there's no limit to how fast you can drive in that case. So if you think about it in intuitive terms, what the word limit means, then it makes more sense that this can only be a finite value. So let's take a look at a graph here. Here we have the limit as x approaches 0 of the function x squared. Okay, so if I again take my, anywhere from the left of x equals 0, if I start to trace the curve, I'm tracing the curve, and I'm tracing the curve, and I'm tracing the curve, it appears that the limit as x approaches 0, coming from the left of x squared, that's my f of x, is equal to 0. Similarly, if I approach it from somewhere on the right, again, it doesn't matter if I start up here or I start down here, we're only focused on x equals 0, so if I start here and move my way in, I also see that the limit as x approaches 0 from the right of x squared is equal to 0 as well. So this means that the limit exists, and we can say that the limit as x approaches 0, because it's the same from the left and the right, I don't have to put the superscript here. I could just say that the limit is 0. We can also simulate this. Let's take a look at a Desmos graph. So here's the graph of y equals x squared, or f of x equals x squared. There's my point 0, 0. So in fact, the function is defined at that point. So I need to be able to trace that curve from either the left or the right and be able to achieve the same limit coming from both directions. So I've just got an ordered pair here that you'll start to see in just a moment as I drag this slider. So all this is doing is I've defined my function f of x. A is negative 10 right now, and I want to plot the point a, comma, f of a. So this is right now plotting the point negative 10, comma, 100. And if I zoom out enough, you'll be able to see it. There it is. Okay, so as I drag that closer to 0, I see what's happening to my y value. It's just decreasing. I don't know how long it's going to decrease, but now as I start to zoom in closer, I can see that, all right, there it goes. It looks like it's going to start leveling off towards 0, and we see that as x gets closer to 0, we can see that this number is starting to slow down. This y value is not dropping by as much anymore, and it appears to be getting closer and closer to 0. Coming from the right-hand side, if I do the same thing, and I start to approach that value, you see my y value is starting to descend below 5, below 3, and you can see that as I approach it from the right, it seems like we're also getting closer to 0. Take a look at another function. Here is the limit as x approaches 0 of 1 over x squared. So you can also do a lot of intuition on this. You may have learned a lot of limit rules. Those limit rules aren't always necessary as long as you think about what you have going on here. So as a denominator becomes closer and closer to 0, 1 divided by something that gets closer and closer and closer to 0 continues to get larger and larger and larger and larger, which is what we see. In fact, from this graph coming from the left, the limit as x approaches 0 from the left of 1 over x squared. So what I have to do is I have to trace the curve. So I'm going to approach this way. I'm going to follow the curve, and the curve is taking me up higher and higher and higher, and that graph disappears, and it appears that that is going to go to infinity. So if you think about it this way, if you square a really, really small negative number, like 1 divided by 0.01 squared, you get 1 over, let's see, that's 0.001, and we see that that becomes a really large number, This should be 0.0001, and that comes out to 10,000. And if I even make that smaller, let's make that negative, 1 divided by negative 0.001 squared. So notice I'm getting closer and closer to making that 0. That's going to come out to 1 divided by negative 0.001 squared, which is going to be 1 million. So you can see that there seems to be no limiting value. We can kind of just see that by the outputs. The outputs are just getting larger and larger as our x value gets smaller and smaller. Now, same thing can be said coming from the right. So the limit as x approaches 0 from the right-hand side of 1 over x squared, we trace that curve. Doesn't matter where we start, as long as it's to the right of x equals 0, we're just going to move our x position this way, which causes us to go up the curve, and it looks like that's going to go to infinity as well. Now, we often categorize two infinities. This is going to the positive infinity as opposed to downwards, negative infinity. Now, you look at these values and like, well, they're the same. But remember, L must be finite. The limit must be finite, not infinite, because, again, infinity is not a limit. So a speed limit of infinity means you can drive as fast as you want. L must be finite, not infinite. So what would we say? We would say that the limit as x approaches 0, the function 1 over x squared is, we could say, a lot of people will just say, right, dne for does not exist, and that would be absolutely valid. Okay, based on the definition of what a limit is. And we could also do that simulation here. So let me just uncheck that function, and I've created a new function called g of x. And then I have a comma g of a plotted. So we can see what happens, and if you just keep track of that ordered pair and its position, so we're starting at negative 10, moving from the left to the right towards 0, and so watch what happens to that output value. It's still fairly small, but pretty soon, got some residue left over there. Check out that value. It's starting to get really, really large, right? It disappears off the screen, it blows up so fast. Now coming from the other side, as we move inward, we see kind of the same thing. Now what happens when a is 0? Well, whenever you plug in 0 into the denominator of 1 over 0, that's undefined, that's infinity. So it doesn't exist even from the graphical perspective. Now here we have a limit. This one's kind of fun. It's a ratio of two functions of x that are exactly the same. And so quantity divided by itself is always 1, right? Well, almost. If we approach intuitively on the graph, so here's x equals 1, if we approach this coming from the left, the limit as x approaches 1, coming from the left of x minus 1 over x minus 1, it appears that if we approach from this side, I'm driving, looks like I get close to x equals 1. Now I'm going to notice a problem here. If I plug in 1 for x, I'm going to have 1 minus 1 over 1 minus 1, which is 0 over 0. So there's actually a hole in that graph right there. Most software won't show it to you because, as mentioned, it's an infinitesimally small hole. We just often draw it so that it's visually obvious. But nonetheless, if I could get to that point, if that crater weren't there, I would land at a value of y equals 1, or so it seems. The limit as x approaches 1 from the right, so coming this way, so taking this curve, and where would I land if that crater were removed? I would land at an output of 1, a y value of 1. Since the limits are the same coming from both directions, I would say the limit as x approaches 1 of this ratio x minus 1 over x minus 1 is equal to 1. So remember from our previous intuitive example, it doesn't have to be the case that the function is defined at that value of x. It just has to seemingly approach the same y value coming from both sides of that x value. The other thing that you might be able to say here is, well, wait a minute, if I do divide x minus 1 by x minus 1, if I do divide that, I get 1. So one of the neat things that happens here is that if you change the value of x and the output is always a 1, then changing x is not going to affect this number, right? There's no x attached to it, so this limit will equal 1. However, if I tried to do f of f of 1, right? So f of 1 is going to be 1 minus 1 over 1 minus 1, which is 0 over 0, which is undefined. So limit still does indeed exist. So we see in the last example where, I called it h of x, so let's call this h of x. In this function, the limit did exist, but the output was undefined. This brings up the notion of continuity, which we've already mentioned in intuitive speak. A function in simple terms is continuous at a point x equals a if you can follow any lengthed path. So that just means that it doesn't matter where I start on the left or where I start on the right. It can be small or large. I could have started here and I still would have had the same result, or here and still have the same result. It didn't matter how far away I started tracing the curve. From some x value on the left of x equals a to some x value on the right of x equals a without encountering a break or a hole in the graph. So you got to be able to drive through that point in order for the function to be continuous. Remember, we're thinking about this as a roadway that we're looking at from a helicopter, and if there's a big hole in the ground, it can't be continuous. That road has a break in it, has a discontinuity. This leads to two mathematical requirements. First, the output at that point, f of a, has to be defined. So remember, all we're saying here is, in graphical speak, or in layman's terms, is that if you have a function, and this is your x-axis and your y-axis, and you have some point right here, x equals a, there are two things that must happen. I have to approach the same value of y coming from both sides, and also the point must be, the y value at x equals a must be the same as both of the limits that I get. So that said in mathematical terms means the limit as x approaches a of the function has to equal the output of the function, and that function has to be finite. It can't be infinite. Which of the three examples considered are continuous at x equals a? So if we look at example 1, well, first of all, you have to have the same limits, which we do. But also now we would need to check for this function, f of x equals x squared, we would want to, scroll down a little too far there. For example 1, where f of x equals x squared, we've already found that the limit as x approaches 0 of x squared, or of f of x, is equal to 0. And so now I just need to check one more requirement. What is f of 0? What is the output when x equals 0? And it's, in fact, 0. So these agree. So this guy is continuous. Similar case for example 2, but in example 2, I wrote x squared. That's what happens when you're a mathematician. You sometimes write the letter x and you immediately start putting exponents on it. So in example 2, we first of all found out that the limit doesn't exist. So if the limit doesn't exist, if you don't approach the same finite value from the left and from the right, then it's not continuous. Simple as that. So this is discontinuous because the limit does not exist. Limit as x approaches 0 of g of x equals 1 over x squared. The limit of g of x is undefined. So we don't even need to check the output, but if you looked at g of 0, that's also undefined. And it's not okay because they're both undefined that you can say, oh yeah, that's continuous now. No, they have to be finite values. So this is discontinuous. And finally, example 3, which we just found out was discontinuous. So example 3 is definitely discontinuous because even though the limit exists at x equals 1, for h of x equals x minus 1 over x minus 1. We had to check two things. We did indeed successfully ascertain that as x approaches 1 of h of x, that we get an output of 1, or a limiting value of 1, but h of 1 is undefined, and since that is clearly not the same as 1, this function is discontinuous. So you can see hopefully the trade-off between the intuition and using some of this mathematical thinking. So here we go into multivariate limits. Multivariate limits are really very, very, very similar. So if you focus on this very careful language that we're using here to talk about limits and to talk about continuity, then it transfers to multivariate limits. So if at this point you're still a little shaky on it, maybe go back and spend a little bit of time reviewing what we've just discussed, because this is going to be the same thing, just with 2 input variables instead of 1. So in the multivariable world, limits are similar. The exception is that in order for a limit to exist at some point, xy equals ab. Oh, wait a minute, what are we saying here? Well, remember we have 3 dimensions. And when you have 3 dimensions, if I have x, y, and z, and now I have some function, some sort of surface over this, I'll just draw I'll try to draw something relatively simple. So let's just say I have some sort of function that looks like this, and I want to see what's going on that function to see if maybe this is a plane. Is it continuous at some point? Let's say that point is over here. Okay, well, how many different directions can I approach that point from? It's not just from the left and from the right, but the reality of the matter is that I could approach that point from here. I could approach that point from here. I could approach it along some curve. I could approach it from here. There are really lots of ways to get to that point. And what we should be visualizing down here is if this point has some x and y coordinate, what that means is that this point is just a point that's elevated above the xy plane. So imagine it's projected down onto the xy plane. So these green curves that we're drawing here are actually some ways in which we're approaching. So like this wiggle here, maybe that wiggle there, that's a projection of that curve segment. And then that little segment means we're coming from maybe this direction. And maybe that means we're actually kind of coming into that point from there. And so we have infinitely many ways. So we want to assess, is the z value that we get here, is the z value the same regardless of which direction I come from? Okay. How many directions are there? There are infinitely many. We can come from any point within the 2-dimensional plane. So you got to think about this 2-dimensional plane here, because we have 2 inputs, and those inputs can co-vary in any way we choose. In a 2-dimensional graph, well, remember there's only 2 axes, and one of them is the output axis. So there's only one way to approach a curve and reach that value of x, right? I could either come from the left or I could come from the right. So furthermore, for a function to be continuous at that point, well, you guessed it, if I'm at that point AB, maybe this is the point xy equals I don't know, 2 in the x direction, 3 in the y direction, that's a 2-dimensional point right there. It must also be the case that not only do you approach the same value coming from all sides, but that point has to not be a hole, right? If there's a hole right there, then there's a discontinuity, which means I can't drive through that point. But if that point is closed and it plugs up that plane, right? So here's an example of, let's say I have a sheet of paper and there's a hole in it, and I'm racing toy cars through here. Well, if I race a toy car into here, it's just going to fall. It's going to fall right through the bottom. And so in order for continuity to exist, we've got to be able to plug that hole up or remove it completely. Okay, so let's take a look at an example. Here we have just some sort of surface, and we want to assess, does it appear to have a limit at the point 0, 0? Well, the question we should really ask is, if I start at this point, for example, right there, and I start to kind of come down the curve, come down the curve, it looks like I land at about a z value of 0. Now if I take another direction, let's say I'm kind of coming up this slope here, and it kind of seems like I land in about the same direction. Now we're using our intuition here. It just appears that regardless of which path we take, imagine this to be a mountain, and we're all walking towards the point x equals 0, y equals 0. Another person could start over here, and they maybe just decide to take this path right here. Well, as they approach x equals 0, y equals 0, it appears that the limit as, well, how do we write this? Well, we can't just say the limit as x approaches 0. We want both x and y to approach 0, so we'll write it like this. We'll just say, as the ordered pair in the xy plane moves closer to 0, 0, of this function z, maybe we call it f of xy, it appears that this approaches 0 from all directions. Now, we don't have a from the left side and from the right side, but we'll learn in a moment that you can actually create a function that goes through the point 0, 0, and you can use that function to create your roadway. So our roadways, or our paths, are going to be created by functions that we invent. And that's kind of a fun process, says the mathematician. What is the limit of, as xy approaches 0, 0, of f of xy, that is, as we get closer to the origin, for the graph of f of xy shown below? Wow, okay, so 0, 0, let's kind of get our bearings here. So 0, x equals 0 is here, y equals 0 is here. It looks like right in the center is where x equals 0 and y equals 0 coincide. All right, well, let's say we're hiking this weird, very, very strange mountain, and I start over here and I try to get to that point. Well, I could, again, carve out any path I want, but as I try to get closer, I'm going to be climbing up this curve. Now that runs out of space, it chops off, but it looks like it's going to continue going upwards, right? So I'm going to be hiking to some peak that's way, way, way up here. So maybe something like that, if we were to continue that function. On the other hand, from this side, it looks like we're also doing the same thing. Maybe as I approach 0, 0, I'm going to have to climb up. But here's where the problem occurs. So we can see that there appears to be a big discontinuity when x equals 0, y equals 0. But let's say another hiker starts here and we say we're all going to meet at the point 0, 0. What's this hiker going to do? Well, maybe they can carve out their path, but as they get to that point, they're going to start coming down, right? So let's just kind of like imagine that that's behind the curve. And this guy's going to kind of go down towards negative infinity. So we observe that the limit as xy approaches 0, 0 for this function, f of xy, is undefined. Now, I put a contour map here as well to illustrate this. So the higher elevations, as you can see, are for, so this portion here corresponds to this segment of the graph. Right, so it kind of looks like this. And that's as x approaches 0 from positive x values, right? And so then this interval here represents this interval over here. So the lighter areas are higher elevations. Rather than using actual contour markers, we're using colors to more easily distinguish elevations. And the darker colors represent lower elevations. So we can see it here as well, that if, for example, this guy who started here starts to kind of carve out his path and then starts to go towards 0, 0, they're going to go to higher and higher and higher elevations. But the person who started over here, and I think we just kind of drew a little wiggle, this person is getting into lower, lower, and lower and lower elevations. And so the limits are not going to be the same coming from both directions. Now we can more formally define this limit. We're not going to be working at a very daunting level with this stuff because there's a lot of cool and interesting things going on. But just to introduce the notion, the definition is kind of the same as the two-dimensional limit. The function f has a limit L at the point AB. So basically the visualizations that we've just drawn is if you could approach that point from any direction for that surface, that you always end up at the same finite L value. If f of xy is as close to L as we please, whenever the distance from the point xy to the point AB is sufficiently small, but not 0. So this gets at a more technical definition of limits, but all we need to worry about is that as we get closer to that point AB in the two-dimensional plane, that point can be anywhere. We want to see, does the limit exist at that point? Well, we just have to be able to approach it from any direction that we want and always achieve the same z value. Imagine this to be a projection in 3 dimensions of our surface. We just have to make sure that if we approach that point from any of those directions that we get to the same value of z. Now, in addition to having a limit, a function is continuous if that limit does exist, right? So that limit exists, and it's equal to the output of the function at that point. The consequence of not having this is, again, going back to that idea of if you have a hole in your 3-dimensional surface, well, it's not continuous because you can't actually drive through that point. Even though everybody will be able to see each other, right, because they'll be getting infinitesimally close to the same z value. So imagine that here's kind of our z-axis, and there's that hole. We can get infinitesimally close to it, but the hole's not filled, and therefore f of AB is undefined. So it's not continuous, but the limit does exist. So to visualize this a little bit better, these ideas and these different paths, here's a little applet that might be helpful. So we'll take a look at this guy here, and I'll show you a little bit about how this applet works and how to use it properly. And here it is. We can make it bigger by clicking on this icon here. There we go. So there are three things to specify. One of them, and I'm going to turn this into a different function. Right now we're looking at the default plot of x squared plus y squared. I'm going to change this to x squared plus y. Okay, so there we have this, this fun-looking parabolic cross-sections from one direction, linear functions from the other, and we want to see, for instance, does the limit exist at the point 0, 0? Okay, so point to approach, I'm going to enter that here. If I change this to like 1, 0, for example, you can see that in the two-dimensional plane, if I look down at it like this, these two graphs are now the same. And there's my point, 1, 0. I don't want to know about the limit at 1, 0. I want to know about the limit at 0, 0. So that's my point of interest, okay? And now I need to figure out how I want to approach that point. So I have to think of a function, any function really, that goes through the point 0, 0. Okay, so any linear function will go through 0, 0 that has a 0 y-intercept. So I could change this to x. And what this is going to do is I can decide how far away I want to start. So if I change this x slider farther away, you can see that what's happening is that in the two-dimensional plane, we're going to start approaching xy equals 0, 0, coming along that line. So visually what that means is watch what happens as we approach 0, 0. So we're coming down now we'd have to maybe zoom out a little more. Sometimes it won't show you the top half of the surface just so the visual doesn't become too convoluted, but just imagine that this surface keeps rolling out like parabolically like it does. So pretty soon you'll see it back down on the surface. This point down here is just a shadow of this top point right here. So watch what happens. So now we're on the surface. You can see that is actually on that three-dimensional surface, and we're approaching it in a linear fashion. So I'll show you. You'll see more of this in a second. So we're approaching it, we're approaching it, we're approaching it. Here's the current point that we're at. So you can see our x values are nearing both being 0. And since y equals x is the function that represents our approach function, the x and the y coordinates are going to be the same. And so as we get closer and closer and closer, you can see now we're at x equals 0.1. Since we're approaching along the function y equals x, the x and the y values are the same. Now I'm going to use my left and right arrows because this helps me do finer tuning and change the x value by just a tenth at a time, or 100th at a time, excuse me, instead of a tenth. And we can see that as we get closer and closer, watch this current point up here, we can see that when we're really, really, really close, right, staring at this thing from above like this, when our point is on the surface and x and y are really, really close to 0, in fact, if I make it 0, I see that the function is actually defined at the point 0, 0 for x and y. Now also I can approach it from the left-hand side. So you can see, again, that's my value that I wish to approach. This visual and this red point, those are just there to ensure that the function that we've chosen as the approach function does indeed go through that point, because if it didn't, then we couldn't talk about the limit at that point. Okay, so as I approach, as my x becomes smaller and smaller and I follow that curve, you can see it coming here from down the curve. And you can see that as we're following in the xy plane along a straight line, that indeed we still get closer to that same value. So let me fine tune this. It looks like from both directions we approach the point 0, 0, 0. But that's only two directions. Did I have to take a line, a linear approach to get there? Not necessarily. Now I couldn't do x plus 1 because x plus 1 doesn't even go through that point. So if we look at it from above, that point along that surface will never actually go through 0, 0, so I can't talk about limits at 0, 0 with that. You can still see that it's following along a line in the xy plane, but the z value is changing parabolically. So it's kind of like we're creating a cross-section out of this point. I'm going to change this back to something similar. I'm going to choose y equals x squared. Okay, so now in this case, if I start far away, it doesn't even matter how far away, but if I start kind of far away from the point that I'm trying to approach, as x becomes small, now notice that if at any point you square the value of x, you should get, so in this case, when x is 2, y is 4, because I've specified that I want to make sure that I get to this point 0, 0 along the curve y equals x squared. Again, this visual shows us that our limiting point, the point that we wish to approach, which is here, is actually on the curve that we're using. So watch what happens as we get closer and closer. The current point seems to be decreasing, and you can see that that three-dimensional purple point, as x approaches 0, seems to be getting closer to the point 0, 0, 0. If I do the same thing coming from the other direction, again, that current point seems to be approaching 0, 0, 0. Now, I also know the function is defined at that point because I can put in 0 for x, since y is going to be the square of x. 0 squared is 0, and then when x and y are both 0, 0 squared plus 0 is 0, so we get a z value of 0 as well. Now, I kind of mentioned that we're parabolically approaching the point 0, 0, and it's easier to see if you look at it from above. If you look at it perfectly from above, you see that that point in 2 dimensions, if I flatten out the z value, it looks like that point is just moving along a parabola. But then keep in mind that there's a third dimension that we can now see, and that third dimension emphasizes the fact that even though that point is moving in a parabolic fashion in the xy plane, it's still moving in sort of a interesting way along the surface itself. So there's a lot going on here. We could choose other functions. Instead of x squared, I know sine of x goes through 0, 0, so let me choose sine of x. And, oh, that's pretty cool. So we could approach it coming from the left, right, along the sine curve, and it looks like that path is also going to bring us closer to a z value of 0. So our current point, even on this function, is the point 0, 0, 0. Same thing here. We seem to be approaching the same point. All of this, we should keep in mind that we're not actually proving anything, we're just visually demonstrating that this works, that it seems that there's a limit. So that begs the mathematical question, how do we do this mathematically? Okay, so you can see that in the xy plane, the shadow of that point forms a parabolic shape, a sinusoidal shape, but then when it's actually moving in the z direction, it seems to be moving parabolically, again, towards the point 0, 0. So there are infinitely many choices for this approach function. And this approach function is really, really useful because as we've mentioned, this observation that x and y are now related. If we know x, we know y, because in this case, y is going to be the sine of the x value. So we can use this technique algebraically to disprove limits. Unfortunately, it isn't always so easy to prove the existence of limits. Now here, we're still looking at the same function, x squared plus y, and we want to maybe look at the point -1, or x is 1, y is -1. Does the limit seem to exist there, based on our intuition and supporting our intuition using the applet? So if I now set my approach point to 1, -1, now again, that's not doing anything in this applet other than just moving that red point, and since our green curve doesn't go through that point, this green curve is not a valid path to take us and evaluate the limit at 1, -1. So one function that you can think of, you can choose straight lines that go through that point. Doesn't necessarily even have to go through the origin, but if I pick negative x, that does go through that point. And so once again, I can approach that point coming from the, you can see that as I approach that point coming from the left side of that line, it seems to be that as x and y approach 1 and negative 1, that z value seems to be getting closer and closer to some number. All right, so we're getting closer, 1, negative 1. Oh, you know, it appears that even at that point, when x is 1 and y is negative 1, we seem to be getting closer to the point 0, 0, 0, 0, 0. Okay, coming from the other side, it also appears, well, heck, we can pretty clearly see visually that there's no break in the graph or anything weird going on, so of course it's going to approach that point. We can pick any point here. We can make this 1, 2, and say, all right, well, it doesn't matter which direction I come from on this surface. It looks like there's nothing weird going on. If I wanted to create an approach function here, I just have to think of a line that goes through that point, so I could pick y equals, we could do 2x, there we go, and now we can approach that point coming from the left, boom. It seems to be the case that as we get there, the z value approaches 3. Same thing coming from the other side. There's no break or anything funky going on. So coming from the left, it appears that we're also approaching the point 1, 2, 3. 2x is not unique. We could have picked something like x squared. All right, well, oh shoot, that doesn't go through it. But if I lifted this parabola up 1 unit, then it would go through it. So there we go. So I can parabolically approach it. You can see there we are, and again, we make it to about the point 1, 2, 3. Doing the same thing coming from the right-hand side. As x approaches 1, we make it to the point 1, 2, 3. So using our support, it appears that this limit is equal to, we said that this approaches 0. And it seems to be doing it from all directions. So one good way to assess it, one easy way to look at, okay, does this surface have limits everywhere, for example? Well, take a look at the function x squared plus y. If that was my function f of x, y, are there any discontinuities or strange jumps in this function? Are there any values that do not produce outputs? Well, no, there's no holes in this graph. There's no value of x that you can't square. And you can always add a number to another number. So the square of a number, think of that as just one number. Think of that as just one number. And I can add any two real numbers together. So those added together will produce a real number. So no discontinuities in this function at all. In this final example here, we clearly see something is going on near the point 0, 0. X squared, y squared over quantity x to the fifth plus 2y to the fifth. We want to show that this is actually an undefined limit at x equals 0, y equals 0. And we can see that pretty closely already, that coming from two arbitrary directions, one over here towards the point x equals 0 looks like it leads us up and down towards a positive infinity, and here it looks like we're going down towards negative infinity. We can't assess this function at x equals 0, y equals 0 because we'll end up with 0 over 0, and that's undefined. So this function is not continuous at the point 0, 0, and we know that already. Let's go ahead and take a look at the graph. So here's our graphical representation. And so as we start to move this around, first of all, one thing that we should notice is the limits of technology. This isn't a tattered graph like a old tattered pants or anything like that. It's just one of the limitations of technology. It's trying to connect the two segments of the graph. And you can see there's some pretty fascinating stuff going on here. There's this little crease in the function. So a lot to be said. Now again, we can choose our approach function. We want to look at 0, 0, so there's our red point. And we want to make sure that our approach function goes through that point. And so we want to pay attention to the current point over here as that x value gets closer to 0. So in this case, y is equal to twice x. So notice the relationship between 1.3 and 2.6. 2.6 is double that. So this is going to help us algebraically, but the observation that really all I have be thinking about is the value of x. I could reduce this to just manipulating the value of x. And we see that as we get closer and closer to x equals 0, y equals 0, let's see what happens here. Well, now it looks like we see that point actually starting to rise. So here, let's take this back a ways. Take this back, and we see that coming along that line, as that point flows closer and closer to x equals 0, y equals 0, it looks like that point is becoming infinitesimally large. All right, so there we are already at 6.15. I could, if I scooted in an extra hundredth of a unit, now it's undefined. Now coming from the opposite side, so let's move over to the opposite side here. So now we're not on this side of this surface, we're coming from the other side, so let's see what happens here as we approach x equals 0, y equals 0. Well, we see that z is negative, and it's becoming increasingly more negative. And now we see that that point is actually moving downwards. It's right here. And unfortunately, that point seems to drop off towards negative infinity. So already we see that we don't have a limit along that line, along that curve. So all we really have to do is demonstrate that the limit is different along two different segments. Let me change this function to the line y equals 0. So I could approach this. There's nothing keeping me from approaching it along the straight line. And in this direction, we see that as here, it looks like z is not changing at all. It looks like the z value is constantly 0. And it actually looks like if we approach it along the line y equals 0, it looks like we're just maintaining a 0 z value. So it looks like the limit coming along this green line, you can actually see it there. There it is. It looks like the z value isn't changing. It's just a perfectly flat surface. And from the other direction, it looks to be the same thing, approaching 0. But again, at 0, 0, 0, 0, we're undefined. We can pick another function, and we could do something like x squared just to get a little bit more of a sense of what's going on here. In this case, as we approach it along the parabolic curve, all kinds of things happening. That point is doing some crazy things, and it seems to be approaching 0 from that direction as well. But it seems like from certain directions, like along the line y equals x, it took us to a totally different point. And that illustrates one of the complexities of these functions. So let's see if we can disprove this limit algebraically. We're convinced that it's undefined. We can also disprove limits algebraically. Now, these approach paths that we've been taking, we can mathematize them and actually use them in limit definitions. So I'm going to draw a two-dimensional graph here. And this two-dimensional graph just demonstrates the approach path that we're going to take. Okay, so if we choose to approach along the line y equals x, so there's approximately the line y equals x, and our approach function, now remember we want to think about the point x equals 0, y equals 0. The z-axis is coming out at us, there's a surface floating above this plane, imagine that. Approach function, let's say y equals x. Well, what does that mean? Well, that means that every single ordered pair along this line will have the same x value as it does the y value. So all the ordered pairs are going to have the form, and you can do one of two ways. You could say x comma x, or you could say y comma y. And the reason you can do that is because they're the same, so you can refer to them by the same letter. Now, what we want to do is we want to take the limit as xy approaches 0, 0 of our function x squared y squared over x to the fifth plus 2y to the fifth. Now, that's our general limit that we want to look at. How we approach that point is up to us. So if we approach it using this approach function, I can write this limit as the point xx approaches 0, 0, and we know it does because we looked at it in the applet and it does go through the point 0, 0. So what this enables us to do is when we look at this function, we can actually say that x and y are the same, and therefore we could reduce this limit to just a one variable limit. So what we're going to do is we're going to say, well, x and y are the same. So this is the same thing as saying the limit as x approaches 0 of the function x squared times x squared over x to the fifth plus 2x to the fifth. Again, because y and x are equal to each other. So in the slider, we saw all we had to do was control the value of x once we specified an approach function, and that would ensure that we approach the point 0, 0. All right, so this means that we have the limit as x approaches 0 of, let's see, x to the fourth over 2x to the fifth. And now if we reduce that a little bit more, that's the same thing as saying 1 over 2x to the fifth as we cancel out the exponents there. And so what happens as this denominator becomes really, 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 really small? Well, this gets closer to, this approaches infinity. So if you divide any number by an infinitesimally small number, the result is infinite. So already we know that the limit doesn't exist because infinity is not a finite value. But let's just demonstrate this. We said another function we could have taken is the function y equals 0. Okay, y equals 0. This was the function y equals x. So now if our approach function is the function y equals 0, let's think about all the ordered pairs on here. Well, all the ordered pairs on this horizontal line are of the form some value of x, which can vary, but where the y value is always 0. So if I look at the limit as our approach function gets closer to the point 0, 0, so this ordered pair just represents the function y equals 0 of x squared y squared over x to the fifth plus 2y to the fifth. Well, y is always 0, therefore that's the same thing as saying the limit as x goes to 0 of x squared times 0 squared over x to the fifth plus 2 times 0 to the fifth. Well, look at that. That's going to be the limit as x approaches 0 of 0 over x to the fifth, which is just 0. And what happens to the number 0 as x changes? Well, the number 0 is always the number of 0, regardless of what x or y are. And therefore, the limit as x approaches 0 of the 0 function is 0. And we already see that, although we already said that this is infinite, these are clearly not the same. And the support was given to us by analyzing the graph of the function. So disproving limits is just picking a few different approach functions and ensuring that, and by the way, if you had picked the third approach function, which was this guy where x equals 0, the reason I want to say that it's not enough just to pick two paths is for that approach function of x equals 0, where x equals 0, let's think about those ordered pairs. Those ordered pairs are all of the form 0, comma something. So every point along the vertical axis has an x value of 0, but a potentially varying value of y. So this is the limit as 0, comma y approaches 0, comma 0 of x squared y squared over x to the fifth plus 2y to the fifth. So in this case, I could reduce this because, okay, x is 0, so that's not changing. So this is really just the limit as y approaches 0. Plug in 0 for x, and you're going to notice we get exactly the same thing. I shouldn't say exactly, but the limit will be exactly the same. And so this is going to be, well, 0. So the limit as y approaches 0 of 0, well, again, this is a constant. So changing the value of y is not going to affect this number at all. So at first sight, what I'm trying to illustrate here is these are the same, but all we had to find was one other path, specifically this one, which led to a different value than these two did. So just because you find two paths that do have the same limit doesn't mean that the limit is the same from all directions. So disproving limits is usually easier than proving limits, because you can often find two different functions that go through the point of interest that have different limits.